stage, and you are the star today. Welcome.
Hi, everyone. Okay,
Just check the screen sharing, okay?
Okay.
By the way, about the law, have you seen Elasticsearch new license?
Yeah, I've seen it.
Another good topic, right? On the next meetup.
Definitely.
Okay, do you see my screen?
Yes.
Yep.
Okay, so let's get started. Today I'm going to introduce some things from stream processing. So there's no time like the present to process data. A little bit about me. I'm Polish Army officer in the rank of captain. I work at National Cybersecurity Center, where I'm leading a team responsible for providing Elastic Stack and data pipelines in Apache Kafka for Security Operations Center. I also work at Senuto when we have fun with Apache Spark at Apache Cassandra. There are a lot of crawlers that crawl the internet, so there's a lot of data to process. I'm also a blogger. I have a blog Wiadro Danych.pl, and I also share my thoughts on Medium. In a spare time, I'm a teacher at Military University of Technology, and I'm also a trainer. I also have my own Elastic Stack course, so if you're interested, you can check it out. It's in Polish, so if you're interested in English version, just let me know. Maybe I'll produce one in the future. So let's start from the batch processing. Let's imagine you have some kind of shop and you process your data in the night. So in the day, you have your organization part, operational part, and in the night, you do some ETL, you do some statistics, and in the morning, analysts go to work and read the papers, read some dashboards, and decision makers make their decisions. Our shop is very cool, people like that. So we scale out. We have now delivery guys, we have trucks, we have cargo cars. Maybe we have some Uber or other kind of delivery service. And we also want to be proactive because our other shops are not sleeping, and everyone wants money, wants customers, wants their service to be the best on the market. So we also introduce some ads and provide some search engine optimization part. So we're getting bigger and bigger, and we scale even more. And as I said, we have the empire on which the sun never sets. So we are an international company, and it's hard to process data in the night because there is no night. So on other part of the world, there is a day. So we have to choose what to do next. We either have a central data center, or we have a distributed data centers all over the world or over the regions. So the first drawback of that data batch processing is that what I called all hands on deck, because when there is a operational part, our resources are utility of our resources are low. But when we run our task, our ETL jobs, our Spark jobs, or whatever we use, we want to get results as much as possible, as soon as possible. So we have big servers, a big farm of servers, and we want to process them as soon as we can. We have to keep up with our time window, because if we are processing the data in the night, so when there is a day, this can be harmful for our analyst part of the company. So we have to provide some, or rather we have to give ourselves some margin of error, because our server can collapse, our job can be killed or something else, and our analyst wants reports in the morning. We also have to provide the possibility of interactive queries for our personnel. So that's also an issue. And however, hardware can be, or another say, hardware should be powerful enough to process that thing in the reasonable time. And regarding hardware, we can buy another server or rent another server or buy another, I would say, the unit of processing power in the cloud. But as like we see in Amdahl's law, even if our power portion of code is 95%, we can speed up to only about 20 times. So this can be misleading. So even if we have some very scalable technology, like Tomek said before about Apache Cassandra, which is highly scalable and nearly linear scalable, but there is also there are always some drawbacks. So operating system overhead, network overhead, management overhead, JVM overhead, sequential, and so on. And sometimes our computation is doesn't depend only on our data in our data center, because sometimes we want to enrich data with some external sources like DNS, like some APIs, some data that is not in our possession. So that can be a problem. And like batch processing, it's not really time sensitive. It's not really good for time sensitive tasks. So if we're running ETL job in the night, we can see the result in the morning, for example. So if there was some kind of a disaster yesterday in the morning, we can see that this happened only the day after. So that can be a problem. So batch processing is good because we know it. The architecture is simple, but maybe in the beginning, because when we scale out, the things get more and more complicated, and we get sure about our data because maybe not all, but most of them are in the data center already. So as I said, it's not ideal for time-sensitive tasks, and we have a all hands on deck resources problem. On the other hand, internet and community advertises stream processing as a near instant results. So it's a silver bullet, it's the best. No, it's not. I think that we think that the load will be distributed over the time, because when we process 24/7, when our data is processed 24/7, we have time to give some computational power to some problems that are hard to parallelize or distribute. But as you see this picture, something in IT, we provide some solution that brings some more problems. So in stream processing, we have inaccurate results. We have to deal with time management or time decisions, like what is the time of the event and what is the time of the processing. This is a new approach for us. So what if application fails? If batch processing task failed, then we can run it again. What if this is stream processing? And how to upgrade that application. So let's say we have version 1 of application that was streaming our data, and now we have to modernize it, provide some new schema, how to do schema evolution, and the most part of it, who will be charged on the all new technology that we bring with the stream processing. So let's say we have new clusters, we have Apache Kafka or some others or some other platform. We have to remember that every tool should have proper maintenance. So let's talk a little bit about architecture. If we go to batch architecture, we have data sources. So let's say this is our application. That application writes data to data store, which can be either data lake like HDFS, AWS S3, or maybe this is just a standard MySQL or other database. Then we have some batch processing, some ETL jobs, or other queries that are sending data to our data warehouse, or basically directly to the client that we are using. If we want to introduce stream processing to our system, we can tackle the Lambda architecture. So we have data sources like before, but now we have to use ingest layer. And in ingest layer, we gather all those events, all those messages, logs, and other data that are coming to our systems. And I mentioned, I have put here Apache Kafka because Apache Kafka is distributed queue, and in Apache Kafka we can have multiple customers. So one client of our Kafka will be a batch layer, so it's again our data lake and our batch processing power. And on the other hand, we have speed layer, so we can use some stream processing engines to provide us with data and with results of those processing things. All those things goes to our serving layer or to our client directly. But here, as you see, we have not only one system, but two systems. And we have to deal with problems related to merging the results. Because what if our speed layer is wrong? So yeah, we can use a batch layer, but let's say our speed layer is producing instantly results from our unbounded stream of events. And we run batch layer every, I don't know, 30 minutes to check if everything is wrong. So what next? What should we do when one result is other than the other? So on the one hand, we solve the problem with time-sensitive tasks, and we have let's say solve the problem with inaccurate results. But now we have two systems, or even three, when we calculate the ingest layer. So resources are double or triple that it was before, and we have to maintain all those things. So there is another architecture which is called Kappa. So we have data sources, we have ingest layer like before, but we don't use batch processing. We do all our stuff in a speed layer, but also we have long-term storage where we can store our events, and if it is necessary, like something broke or we have to recalculate something, we can go back and grab those events and pre-process it. So let's talk about streaming platforms. I have mentioned already Apache Kafka, which is, in my opinion, the most popular in big data world distributed queue. But there are also Apache Pulsar, Apache ActiveMQ, Redis Streams, RabbitMQ, which is known, I think, better in more software development ecosystems. Some, of course, cloud-native solutions, or even VernMQ if you're familiar with MQTT protocol and IoT systems. So there are a lot of options, but we are talking about streams. What if we don't have Apache Kafka or any other platform? What if we use single or multiple SQL servers, which can be a Microsoft SQL server, MySQL, Postgres, or some Oracle technology? Then we can use change data capture. And with data capture, we can make a stream from our database. So we are capturing events like simple CRUD, so create, update, delete, and so on. So we grab those events and put them into our streaming platform. So on the slide, you can see that I've put the Debezium here. Debezium is an open source Kafka Connect plugin, so you can use it to capture data from your database. If this is MySQL, you can use it right now. If this is Postgres or Cassandra, you should put some little agents to help analyze the write-ahead block and so on. So you can provide this solution, and we can use change data capture not only to make stream from our database, but also to provide some integration and synchronization between our databases or our systems. So there are two approaches. One is log-based, like Debezium. So we're listening to the events that are happening in our database. And there is second approach, query-based. So let's say we have some kind of application like Logstash and so on, which can talk by, for example, JDBC protocol with databases. And in some interval, Logstash can ask database for some specific table. Hey, database, bring me some records that happened before that and after that point of the time. But that can be stressful for the database, so it's not the best solution. It's log-based is better, like Debezium. And the second problem with query-based solution regarding data capture is problem of deleting. So imagine that we have Logstash that is getting log records from database, and someone deletes a record in a database. It's hard to query a deleted record in a database. So we have to do some magic tricks like soft deletes. So we have we delete record in a database by putting some flag on it. So we simply add a new column with Boolean flag that this record is deleted, and some other job is running, for example, in the night and deleting those records in all our databases. Okay, so we have our data sources. This can be logs, this can be clickstream, or any other, let's say, not strict business data. We can use change data capture to make a stream from our database, but also we have events in our applications. So either we use monolithic architecture or microservice architecture, there are events in our application. So one microservice can communicate with another microservice and saying, hey, someone clicked this, so make that. And we also should take that in mind. So let's start with monolithic architecture. We have application that is talking with some database. And after some time, we have a need to add some search index like Elasticsearch or Solr. And we have cache, which is, for example, Redis or Memcache. And like Gunnar said, friends don't let friends do dual write. So we have a problem now because our application is responsible for writing to not only database, but also to Elasticsearch and to Redis. So we should make that better because it's not optimal right now. And when microservice goes, because some architect in our company say that, hey, microservices are cool, everyone is talking about microservices, so let's split our application and make some microservices. So now every application, so every microservice has its own database. So our data is sharded across our data center, not only physically, but also logically. And those databases can be in various types. But there are, after some time, there are even some more applications. Everything is more complicated. We have polypersistent. We have not only relational database, we have Cassandra, we have Redis, we have search index, and so on and so on. So everything is getting more and more complicated, and every microservice is talking to each other. So maybe let's use some kind of stream processing platform like Apache Kafka to make some communication platform to share information between microservices. And with that approach, we have a little bit easier way. We are in a better way to provide some ETL and synchronize those databases, or simply put some information in our data warehouse or data lake in a way that the data is less normalized and more denormalized, so we can process that data better later. So now let's talk about stream processing engines. As you can see, there are a lot of them, and I won't discuss here which is the best or which is the worst. I would only say that if you're familiar with Spark, maybe you should use Spark structured streaming because this is the natural way. it's easier to go from batch to micro batch approach in Spark. If you're interested in more streaming, not micro batch, but streaming approach, you can use Flink, Storm, or Samza, or even Beam, which is more unified way. If you're familiar with Kafka, you can use Kafka Streams or KSQLDB, which is a wrapper around Kafka Streams. And you can use SQL to provide some streams in your system. Or if you like Python, you can use Faust or any other, I would say, cloud thing regarding stream processing. But whether you use one or other technology, there are two ways to create your applications. One is without test. So let's say you have chosen Kafka. You run Kafka, you run console producer, you run console consumer, you write some code, then you compile it, you insert events, check result, insert event, check results, and so on and so on. Another way is to write unit tests, and I encourage you to provide some unit tests in your streaming application, because it makes development much easier and much faster. So you don't have so much dependencies when you're developing. You don't even need a Kafka if you're using Kafka streams. As you see on the slide, we can use unit tests to mock our streaming platform and focus on the logic of our application. So let's maybe talk a little bit more generic than focusing on specific technology. Right now, I would like to remind you of fallacies of distributed computing, because if we are developing some applications, we like to look at things from the higher perspective, so from the higher abstraction. So we don't see that there is a network, there are people, there are bits and bytes, there are cables, and if you come down to data center, you see a lot of servers, a lot of noise, and a lot of things that can go wrong. So regarding stream processing, we have stateless approach. So it doesn't depend on the past, and you don't have to worry about nothing. I was joking. So you still have to worry about some things, because as I mentioned in slide before, there are many things that can go wrong. And for example, you can get event from a message queue not only once, but twice or more, or maybe you just don't get anything. So if you plan your processing operators to be independent, it will be easier for you in the future. So there are also things like poison pills and dead letter queue. So what is poison pill? Imagine like your application stream processing app is like that Pac-Man, which is constantly consuming some events. And poison pills are those ghosts from Pac-Man. If you eat them in the wrong way, or if you don't get prepared to eat them, you can be killed. And problem with, for example, Kafka streams and Apache Kafka is that when you don't try catch something, then your application will throw error and will simply won't work. So you run that application again, but that poison pill is still in your queue. So we have to remember that there is a mechanism called dead letter queue, which can be used to put those poison pills on the side to watch them later, because all humans make mistake. It's hard to try catch every piece of code, and sometimes to heal our application, we have to rewrite it, we have to put some patch, or we have to get rid of that record that is broke, that is harmful for our application. So another way of stream processing are stateful operations, which depends on the path. Here is a matter of processing time versus event time. And if you're using Elasticsearch, there's a timestamp and event created fields. And another thing is that sometimes we want to join streams. So there is an issue that there is a problem of processing time in one stream and the second stream, and now we want to join them, and and it gets more and more complicated. So let's say we have a simple DAG. There's a stream of XYZ events and ABC events. So in the first XYZ events, we want to mask those events because let's say this is some GPDR related things like names, surnames, etc. We only want to get those essence of business event. And in the second, we just to filter something. Then we can use branch. We can split those events to type A and type B. And we can join one, or we can do some stats. And that's the way it is. So let's come back to issue with time, processing time, and event time. So this is the ideal. This is the ideal solution, the ideal situation when processing time is event time. So let's say we are at this point of time, and everything is good. Everything came not late, not earlier. It's great. But in reality, we have late events and we have early events. So life is life. So maybe there was a connection loss. Maybe someone is using their smartphone and the connectivity is not the best. So life is life. We have to prepare for everything. So let's talk about windows, time windows on which we would provide some aggregations. The first type of window is tumbling window. So let's say we want to give results for a very 15 minutes. And when we calculate everything from this 15 minutes, we want to calculate everything from the next 15 minutes and so on. Another type of window is hopping window. So now our windows are overlapping. We have one, we have second, third, fourth, and for example, we can do some average aggregation to check if the threshold of our something is good. Next, we have sliding window. So we have a statement that give me the result when something is more, less, or whatever in the last 10 minutes. So we have condition. And again, we have a window that can overlap to other window. And another type of window is session window. So give me the results that occur within 2 minutes. Let's say our application have users. So it's very good to have users. And we want to detect how many things related to our business user is doing in one session. So let's say we use mobile phone, we open Facebook, we do some clicks, we watch some pages, we read some posts, and we want to know how much posts that or how much ads that user is seeing in one session on average. So now let's talk about triggers. So let's assume that it's 15 minutes regarding time, and we are in processing time. So that line is going from the bottom to the top, and event time is to the right. So right now, if we are at 15 minutes time, we have processed that, hey, in the first window, we have calculated that the sum of those events is 14. Okay, cool, we can save that in database or some, I don't know, Elasticsearch or Druid or whatever you use. But hey, after another 15 minutes, the late events came. And now it looks like it's not 14, it's 17. But those previous score was already sent to database. So what now? So now we have to decide what we do with accumulation. Because if our, I would say, target database that our results of our processing stream processing app is going, we have to decide what we do with late results. Should we recompute? Should we discard them? Should we multiply them? Should we send them anyway? Because if our output database can get those events, get those results, and can handle that. Hey, I was saying that window was 14, but now it's 17. Oh, okay. I will just update the view that our analysts look, and everything will be okay. But that is the issue that we should think about. So now let's talk about watermarks. As you have seen here, how much should we wait? So in a perfect situation, we should wait something a little bit here. So we should wait till all our late events come to our streaming processing platform, and then compute them, and then continue to process another windows. But sometimes we just can't wait any longer, because let's say if we have a 5-minute window, we want wait, for example, hour to be 100% sure that all those events are already in our streaming system. If this is a window of a day, then we can wait 1 hour, because regarding the percent, it's not that much. But if it's 5 minutes, then we should wait, I don't know. It all depends on your case. How much you can wait for those results. If the longer you wait, the more sure you are that you have all those events and your results are correct. So let's talk about case study. I was working 3 or 4 years ago in some company, and there was a application that was monitoring vehicles regarding some transit all over the Poland. There were route traces, and there were driver statistics, and there was single SQL server, I mean logical single SQL server, not physical SQL server, and there were also application, or rather multiple applications, but that I'm saying about single desktop application that was used to monitor those vehicles. And model in our database was normalized. So there are some vehicles. There was not Lamborghinis, but some transit. And there is our app. Oh, sorry, I have to move this window from Zoom. So there are problems with those applications. There was problems with this application because that was a single application that was continuously providing multi-join queries on the database. So it was very slow. In the morning, when there were not a lot of cars, it was okay. In the evening or in the night, it was also okay. But in the noon, it was terrible, because every query hit multiple tables. Data was normalized, wasn't denormalized, and there was very poor caching and some statistics when calculated in the application. So what could be better in that application? So another thing that I want to say that when you gather records from your cars, so the GPS signal, so the speed and so on, you do that in some, let's say, intervals. And when you do that in intervals, then the trace that you're drawing in your application in your map is not smooth. So you want to smoothen those traces using some external APIs. So let's say this is OSRM, which is open source routing machine, which you can install on your in your data center on your server, which can provide some routing API. You can use Graph-Hopper, you can use Google Maps API, but all those services operate on your data. So if your data is a little bit inaccurate, then you have problem. So what if you could not only do this before you ingest this data to your database, but what if you could correct that data or discard that data to make your data more, let's say, beautiful, more not error. And I have seen that even if you use some, let's say, public APIs, that is API of Warsaw Public Transport, everything lies. So every sensor eventually can lie to you. So the error tape is still going on. So let's discuss a better way to make this application going. So at first, let's introduce our ingestion layer. So we have our Apache Kafka or any other queue. And this arrow means that we are doing some stream processing here. So maybe we are doing some filtering. We want to discard those error records. Maybe this is some kind of magic machine learning thing that will provide us with better results, or maybe even correct our GPS records, our GPS signal. Okay, so then those events are coming to our database, but not in the way that it was before, but in the normalized way. So we don't have to continuously run multiple joint queries from our application. We can use just simple select from a single table, and everything should be a little smoother and a lot faster already. Another step is to introduce some kind of, let's say, real-time approach. So we can use another database, which is, let's say, RefingDB, or we use SignalR or WebSocket server. SignalR is technology from Microsoft.NET Core. So when we have Apache Kafka or other streaming platform, we can decouple some logical parts to some other places. So maybe let's introduce another, let's say, brick in our building, which can be Redis for caching. Or maybe we should even provide some search indexes, publish some information to Google or to Apple. So let's say if we want to notify our drivers that, hey, your speed is too big, you're speeding, or you're late, or you should be aware of something. And I forgot something. And then we can distribute those events or those messages to multiple systems, even to analytics systems. So maybe our analytics want to know if this route is better, or this route is getting worse in the morning, but later it's better and better. Or even we can provide some, let's say, machine learning thing. And I mean that we can provide some automatic suggestions to our drivers that, hey, maybe you should look that way. And so on. We can use our another microservice. We can connect another microservice, and we can do everything on top of stream processing platform and provide some better way to gather those data, save them in, for example, data lake, and do even in a batch manner, batch style, do some magic about it and provide some value from those data. And thanks for your attention. That's that's all what I was all what I was wanting to say to you. If you're interested in my course, here's the link. You can catch me on Twitter, on LinkedIn. You can mail me. If you have any questions, or you or you didn't understood me, you can ask me a question.
Okay, thank you so much. It's great. Okay, so I don't see any questions. There was a small discussion. I would suggest temporal tables mechanism instead of change data capture, strictly for SQL Server, so about historization of data.
Mm-hmm.
So if anyone has any question, you can raise your hand or type on chat.